So, a couple of announcements. I hope you guys have done quiz 1. Quiz 1 is due by 11 a.m. today. So you got about 1 hour left. Well, you got exactly 1 hour left. So if you haven't done quiz 1, please try to do it before 11 a.m. today, right? And the second announcement is about the tutorials this week. There were 6 tutorials this week, and I hope you guys attended one of them. And if you have not attended any of them, you can view the tutorial sessions here. These are the videos. These are the videos for the 6 tutorial sessions, as you can see, right? And there's also a video that gives the full solutions. This video here gives the full solutions to all the questions in the tutorial sheet. I mean, during the tutorials, it's difficult to go through all the questions because of the time, right? And you can look at this video here, which gives the full solutions to all the questions, this last video here. And there's also the typed solution. These are the typed solutions to the tutorial sheet. And this is the handwritten solutions, which sometimes is more detailed than the typed solution. And then you have these 6 sessions and the 6 videos plus the video giving the full solutions to all the questions. All right, guys, so this was the quiz that was due this week, well, by 11 a.m. today. So please, if you have not done quiz 1, please do so before 11. Right? You will get an email from me in a couple of hours' time or so, giving the mark and what the correct answer is and how I got the correct answer. Right? Okay. And I hope you guys look through these 4 videos. I asked you guys to watch these 4 videos before coming today. The first video is on summary statistics. This one, graphical displays, normal distribution, and the binomial distribution, right? Okay, so what I will do now is to go through these 4 videos quickly, and then do some examples, right? Okay, so let's start with the summary statistics one, right? So suppose you have the data x1 to xn. There are a variety of summary statistics. The first one is known as order statistics, where you arrange the data from the smallest to the largest. The second one is the sample mean, which is simply the average. The third one is the sample median, which is defined differently depending on when n, the sample size. N is the sample size is odd or even, right? So if n is an odd number, then it's the middle number. The median is the middle number. If n is even, then it's the average of the 2 middle numbers, right? Then the pth quartile or the quartile or the quantile is defined by this equation here, where r prime is the integer part of p times n plus 1, and r is p times n plus 1. I hope you know what an integer part is. Like when I put a brackets around x, that denotes the integer part. So for example, the integer part of 1.9 is 1. The integer part of 9.5 is 9. And if r prime is 0, then the quantile is equal to the smallest data. And if r prime is n, then the quantile or the quartile is equal to the largest data, right? Okay, so then this first quartile or the quantile is defined as q at 0.25. The third quartile is defined as q at 0.75. And in general, a quantile or quartile is defined by this equation here, right? Okay. Then the sample variance, there are 2 formulas for the sample variance. This one is the biased version where you divide by n. This is the unbiased version, which is dividing by n minus 1. So Usually the unbiased version is better than the biased version, right? But sometimes you have to use the biased version. I will explain in a minute later. And these are alternative formulas for these two, right? And this is the formulas for the sample standard deviation. It's just simply the square root of the sample variance, right? Next is the sample range. Sample range is the difference between the maximum and the minimum, right? So this is the largest data, this is the smallest data. You take the difference. The sample interquartile range is the difference between Q at 0.75, which is the third quartile, and Q at 0.25, which is the first quartile, right? Now, these are the R commands. I will skip this. I already showed you this in the video. I hope you guys watched the 4 videos I asked you guys to do, right? And this is an example I did. I hope you guys watched this example. If you have questions, please feel free to email me. This is the proof of star. That is the proof that the sample median is given by these two formulae, depending on when n is even or odd, right? So I hope you guys looked at this proof. And if you did not understand the proof, contact me 24/7, right? This is the proof for the formula for sample median, right? And this is the proof that the sample variance, the biased version of the sample variance, can be written as this, right? And once again, I hope you guys looked at this proof. If you did not understand the proof, contact me 24/7, okay? And this is the proof of the formula that the sample variance, the unbiased version, can also be written in this form, right? So this is the proof. Okay, now next one is graphical displays. There are many different ways of displaying data. I will talk about 3 different ways: box plot, bar plot, and histogram. So let's start with box plot. This is more detailed than is it the right way? Oh yeah. This is more detailed than the version that I actually put in the video. I will scan a copy of this and post it later today in the course website. So a box plot looks like this. The middle line is the median. This line is the first quartile. This is the third quartile. The red arrow is the distance is 1.5 times IQR. So this line here is known as the lower fence, right? This is known as the lower fence, and this red arrow here is again 1.5 times IQR, and this line here is known as the upper fence. And anything that goes below the lower fence or above the upper fence is known as an outlier. So if X is a data that is greater than the upper fence or smaller than the lower fence, then it's referred to as an outlier. It's referred to as an outlier, right? Okay, and one more thing, there's something called the lower adjacent, and there's something called the upper adjacent. The lower adjacent is the smallest data that is greater than the lower fence, right? Whereas the upper adjacent is the largest data that is less than the upper fence, right? So there are a few things you need to know about the box plot. There is the lower fence, then the lower adjacent, then the first quartile, the median, the third quartile, the upper adjacent, and the upper fence, right? So all those items that I just talked about make up what is known as a box plot, right? Okay, is that clear? I mean, this picture is a little bit more detailed than the picture I put in the video. So I'll make a copy of this and post it right in the website. Okay. Yeah. By the way, the command for the command for in R, the command for box plot is simply box plot in brackets the data that X is the data, is an object that contains the data. Right. Next is a bar plot, like the command is this. So for example, if you have data on the different parties in the UK, like Conservative, Labour, then that bar plot is a good way of representing such a data. So you can see immediately which party got the highest number of votes, right? And the next is a histogram. Histogram is basically, it tells you the distribution of the data, whether it's symmetric, whether it's skewed to the left or the skewed to the right, things like that. This is the command for a histogram, right? So if a histogram looks more or less like this, then this is symmetric. It looks more like the normal distribution. If a histogram looks something like this, then the distribution is skewed, right? So for example, if you have a histogram looking like this, then the distribution is positively skewed, right? Whereas if you have a distribution looking like this, it's negatively skewed, right? I'm sure you know this stuff anyway. All right, the next video I'm going to talk about is the normal distribution. I'm sure you talked about this in probability 1, the normal distribution. The density or the PDF, this is a continuous distribution. So the density or the PDF is given by this. There are two parameters. Mu is the mean parameter, sigma is the standard deviation parameter. This is the CDF of a normal distribution. Phi denotes the CDF of standard normal, and this is a property of the CDF phi. This is an example on how to read the values of the function phi, and there's a table for that. So this is the table that you should use to read the values of the function phi. I explained that in the video, so I hope you did. You watched the video, guys. I hope you did. The next thing is the R commands. So the command dnorm computes the density of a normal random variable, whereas the command pnorm computes the CDF of a normal variable. So mean denotes the value of the mean parameter. ST denotes the value of the standard deviation parameter. So this is the mu, and this is the sigma, right? Some properties of a normal variable are: this is the mean, the variance, standard deviation. If you have two independent normal variables, then their linear combination is also normal. In general, if you have n independent normal variables, then their linear combination is also normal. And if you have n IID variables that are normal, then the sample mean is also normal. And this is known as the standardization property, that if x is normal, then this standardization gives what is known as the standard. This is the standard normal variable, right? Estimation. Estimation is right. Suppose you have a data that is a random sample from a normal distribution, then it can be shown it can be shown, but I don't expect you to know this for this course. I mean, in the second, when you move on to year 2, you will learn how to prove that the estimate for mu is equal to the sample mean, and the estimate for sigma squared is equal to this. As you can see, this is a biased version of the sample variance, not the unbiased. This is what I said earlier, that sometimes you have to use the biased version because it turns out to be the estimator for sigma squared, right? You know what I'm saying? Yeah, okay. And this is one more example. I hope you looked at the examples. The final video, guys, is the video on the binomial distribution, right? So this is the notation for a binomial. This is the probability mass function for the binomial. I'm sure you guys seen the binomial in probability 1 or some other course you took in the past. This is the notation, and the CDF of a binomial is given by this equation here, right? These are two properties of a binomial. The mean and the variance are given by MP and MP times 1 minus P, right? The R commands, the command for computing the PMF of a binomial is dbinom, where size denotes the value of M, probability denotes the value of P, right? And the CDF for computing a binomial is P-binom, P-B-I-N-O-M, right? Then I did some examples, I guess, estimation, right? If you have a random sample, from a binomial distribution with parameters M and P, then estimator for P is given by this, right? Okay. Again, I don't expect you to know the derivation of this formula. Once again, when you move on to year 2, you will learn how to derive this, right? Okay. And these are some examples. Example 2, example 3. So I have gone through them quickly, but I hope you guys, all of you guys watched the videos, right? Do you have any questions on the 4 videos before I go ahead? Come on, guys. Are you all right? Do you have any questions, guys? No? Any questions on the 4 videos I asked you to guys? These 4 videos. Did you all watch those 4 videos? Yeah. Any questions, guys? Yes. No. I mean, feel free to ask me any questions you guys have. I'm happy to go over stuff you may not have understood clearly. Yeah. All right. If you don't have any questions, let me do some examples in the remaining time. Okay. Right. So example 1. Suppose you have the following data. The question is to compute the summary statistics, right? So we start with the order. Okay, the first thing is the order statistics, right? So order statistics simply means that you order the data from the smallest value to the largest value. The smallest data point is 0, then is 1, then is 2, then is, right? So this is your yeah. Okay. And next one is the mean. Mean is simply the average of the data. So it's going to be 1 plus 0 plus 3 plus 2 divided by 4, which is equal to 1.5. C, next one is the median. Median is in this case you have 4 data points, so So you take the two middle numbers and divide by 2. So the two middle numbers are 1 and 2, and you divide that by 2. So this is going to be 1.5. So in this case, the mean and the median are equal. So that means that the distribution is symmetric, right? Next, we want to find the first quartile. All right, to find the first quartile, remember, is Q at 0.25. That's the first quartile, right? So to find that, you need to first find R prime. Remember, R prime is defined as n times p plus 1, which is 4. Sorry. Is 5 times 0.25, yeah, which is the integer part of 1.25, which is 1. Remember, n is 4, so n plus 1 is 5, okay? So using the formula that I showed you earlier, if you don't remember where it comes from, or maybe I can show it here. The formula that I'm using is this one here. This is the formula on the very top of this, right? So if you use that formula, you can use Q at 0.25 x, yeah? Then you have 1.25, take away 1. Then in brackets, you have x at 2 minus x at 1. You see, you follow what I'm doing, right? Yeah. So if you sum in the numbers into this equation. So x, the smallest data is 0. This is 0.25 times the second smallest data is 1. So it's 1 minus 0. All right. So this will be equal to 0.25. So the first quartile is equal to 0.25. You see how I used it, right? Is that clear, guys, or not? Yeah, So the next one is the third quartile. Third quartile is Q at 0.75. Yeah. So in this case, R prime is going to be 5 times 0.75, which is equal to the integer part of 3.75, which is equal to 3. Yeah. All right. So using this formula one more time, the formula in the very top of the computer slide, yeah, you can see Q at 0.75 is equal to x right? Okay. So if you do the math on this, you will get this to be equal to 2.75. All right, so the third quartile is equal to 2.75, right? Next one is the sample variance. The sample variance, remember there are two formulas for sample variance. I'm going to use both formulas, right? So if you use the unbiased version, right, which has n minus 1 in the bottom, it's going to be 4 minus 1, right? Then in brackets, it's going to be 0 minus, so I'm using the unbiased version here, which is in the very top of this 1 over n minus 1 times this. All right, so it's going to be 0 minus, the mean is 1.5 squared. right? And if you do the math on this, you will get this to be equal to 1.666667. So this is the unbiased estimate. Yeah. And if you use the biased estimate, in this case you will divide by 4, right? If you use the biased version, which is the equation in the very top of this, right, you will get this, and if you work this out, this will be equal to 1.25. So this is the biased estimate of the sample variance. All right, you follow me? Yeah. All right, the next is, so that's G. Next one is the standard deviation. Standard deviation is simply the square root of the variance. So it will be the square root of 1.666. This is the unbiased estimate, or the square root of 1.25, which is the biased estimate, right? So this is the unbiased estimate, or the biased estimate, right? And the next one is H, which is the range. Remember, range is the difference between the largest data point and the smallest data point, which is, in this case, is 3 take away 0, right, which is 3. And the next one is IQR, or interquartile. Interquartile range is the difference between the third quartile and the first quartile. So right, and if you take the difference, is 2.5. All right, so we worked out all the summary statistics that we talked about in this course so far, right? Okay. Right. So that's example 1. Example 2 I'm going to talk about is example 2 is the following. Example 2 is about, okay, consider the following data. So you have the following data: 0.98, minus 1.20, minus 0.65, 0.16, 1.1, minus 1.8, sorry, 0.12, 0.6. Oh, I left out one thing here. 0.18, 0.32, minus 0.7, 0.94. Right, so we've got 10 data points, right? The question is to draw the histogram All right, draw the histogram with interval width equal to 0.5. Now remember, I showed you what a histogram is. Let me show you again. A histogram looks something like this, right? I mean, you can do it in R, but if you want to construct a histogram by hand, this is what you need to do, right? The first thing is you need to create a table with the following columns. All right, we are looking at an interval width of 0.5, which means that each interval should have this width. So the smallest data point here, the smallest data point is minus 1.8, right? Okay, so it's okay to have an interval starting from, say, -2 and going. So this is the first interval will be from -2 to -1.5, then -1.5 to -1. So it's closed on one side and open on the other side, right? -1 to -0.5, -0.5 to 0, 0 to 0.5, 0.5 to 1, and finally 1 to 1.5, right? As you can see, the largest data point is 1.1, so it will fall in this interval, right? Now what I'm going to do is look at each of these intervals and count how many of the data fall in each of these intervals. For this interval, there is one data point. I mean, you can count. I'm sure you know how to do it. And for this interval, you have one data point. For this interval, you have 2. For this data point, you have 0. For this interval, you have 3, 2, and 1. Right? So that's the frequency. It's the number of data points that fall within each interval. And the density is defined as the frequency. All right, let me write it down here. The density is defined as follows. Density is equal to the frequency column times divided by the interval width multiplied by the number of data. Right? Okay, so the frequency column divided by the interval width multiplied by the number of data. The number of data in this example is 10, right? And the interval width is 0.5. So 0.5 times 10 is 5, okay? All right, so the density will be 1 divided by 5, 1 divided by 5, 2 divided by 5, 0, 3 divided by 5, 2 divided by 5, and 1 divided by 5. All right? You see what I've done, right? I used this formula here. So frequency divided by the interval width times the number of data, which is, the number of data is 10 here because you had 10 data points. The interval width is 0.5, right? So the next thing you need to do is just to plot the frequency versus the interval. So if you do that, this is what you will get. This is the plot that you will get. You should plot frequency on the y-axis and the intervals on the x-axis. This is what you will get, right? And if you plot the density versus interval, then this is what you will get. So here you have the density on the y-axis and the interval on the x-axis. And the reason I have shaded this is to the purpose of density. I'm sure you did this in probability 1. density means that the area below the curve, or the area below the picture that you have drawn must add up to 1, right? So you should take the area of the shaded region here. You should take the area of the shaded region here. It must be equal to 1, because as you know, the density is something that should integrate or sum to 1, right? Okay. All right. So the next thing, all right, so that's example 2. So I'll put it here. Are you guys okay with example 2? Yeah? All right. The next example I'm going to talk about is example 3. Example 3. So consider the following data, which is the same data as so this is the same data that I used. This is the same data that I used in example 2, right? The question is to draw the corresponding box plot, right? So I'm going to use to draw a box plot, you need to compute a few things. You need to compute the median, right? You need to compute the first quartile. You need to compute the third quartile. And you need to compute the IQR, or interquartile range. So you need to compute these 4 things in order to draw a box plot. Because I don't have the time, I will just write down what the numbers are, okay? I'm sure you can verify them when you have time. But let me write down what the answers are. These are the numbers that you will get if you work out these 4 things, right? And also you need to remember the picture that I showed you earlier. Let me get it for you. In order to draw a box plot, you need here we are. This is the picture that we need to follow in order to draw a box plot. So you need several things. You need the lower fence, right? You need the lower adjacent. You need the first quartile, median, the third quartile, the upper adjacent, and the upper fence, right? So the lower fence is defined as 1.5 IQR from this, right? That's the distance between the lower fence and the first quartile. And similarly, the upper fence is defined as the 1.5 IQR from the third quartile, right? So in order to work out the lower fence, what we need to do is the following. You need to, from the first quartile, take away 1.5 multiplied by IQR. That will give you the lower fence. So this will be, if you work it out, if you have a calculator, you can do it, but I have already done it. This is what you will get. And the upper fence is defined as the third quartile plus 1.5 times IQR, right? Which you can work it out is to be 3.6125. So these are the 6 items that you need in order to draw a box plot. The median, the first quartile, the third quartile, the IQR, the lower fence, the upper fence. All right, now if you draw the box plot, it will look something like this. I know it doesn't look it will look some, I hope you can see this, right? Excuse me for my handwriting, it's not very clear, but so you can see the median is 0.17. The first quartile is minus 0.825. The third quartile is 0.95. This is 0.95. The lower fence, which is this one, is minus 3.4875. The upper fence, which is this one, is 3.6125. And the lower adjacent is the smallest data that is greater than the lower fence. So if you look at the data set here, this is the data set. The smallest data point that is greater than minus 3.4875 is minus 1.8. So therefore, the lower adjacent is equal to minus 1.8, right? And similarly, the upper adjacent is the largest data point that is less than the upper fence. The upper fence is 3.6125, and the largest data point that is less than that is 1.1, right? Yeah, so therefore the upper adjacent is equal to 1.1, right? All right, I hope you can read this box plot which I have drawn. Anyway, I will scan this just after the course, after this hour, then I will put it online. You can see it, right? So that's 3 examples. The fourth example, if I have time today, I may not have the time, but if I have the fourth example, this is example number 4. Any questions on the 3 examples I did so far? Any questions or not? Okay. Suppose right. So this is a proof question, right? So you have a random sample from a population with the population mean equal to mu and the population variance equal to sigma squared. And the question is to show that the expected value of, remember, this is the unbiased version of sample variance. So the question is to show that the expected value of the unbiased version of the sample variance is equal to the population variance, right? And this is precisely why it's known as the unbiased version, because of the fact that its expected value is equal to the population variance. That's what you would expect. If an estimator is a good estimator, then you would expect the expected value of that estimator to be equal to the population parameter, right? I would like you to show this. There are 2 steps. I'm not sure if I have the time to complete it. There are 2 steps to do this. There are 2 steps. In order to show this, you need to do 2 things, right? First, first you must show that the first step is to show that you must show the following, that is the sum of xi minus x bar squared, right, is equal to the sum of xi minus mu squared plus n times x bar minus mu squared, right? That's the first step you must show. And the second step, I'm just trying to give you a hint, I mean, because I'm running out of time, so I may not have the time to show this, all right? The second thing you must realize is that the expected value of xi minus mu squared, right, by definition, right, this is the variance of xi, and the variance of xi we are assuming is equal to sigma squared, right? And also the expected value of x bar minus mu squared, right, is by definition is the variance of x bar. And you may remember from last Friday I showed you that the variance of x bar is equal to what? Do you guys remember? I'm sure you're so young, guys, you should have a better memory than I do. What did I show it was equal to? Huh? Sigma squared over n. Yeah, exactly. Right. So these are the so in order to prove this statement here, first you need to show that this guy can be written as this plus this, and then use the fact that the expected value of this guy is equal to sigma squared, and the expected value of this guy is equal to sigma squared by n, right? So it's not hard to prove, but I don't think I will be able to finish it if I start today, right? So please, when you have time, try to prove it, okay? And of course, if you have difficulties, you are most welcome to contact me 24/7. And before you leave, I would like it to show you something. Next week is we have computer classes next week. So these are the sessions for next week. There will be computer classes at these times. All of them will be based in Alan Turing G105, which is the computer cluster. I'm sure you know where it is, right? And the sheet that you need to work through is this one. So this is the sheet that you need to work through during the tutorial next week, right? Okay, so please try to go through this. When you have time, or if you have time, please try to go through this, right? And okay, and so I'll see you guys next week, and have a great weekend. And any questions you have about this course, please feel free to contact me, right? By email, Skype, Zoom, or phone, right? Okay. Yeah.
When we worked out the first quartile, it was a positive number. Oh, it was a negative to begin with?
Negative, yeah.
Yeah, I didn't.
Yeah, you have a question.
So, can you tell me the formula for IQR?
IQR is just the difference between the first quartile and the third quartile.
Oh, that's the range.
No, the range is the maximum minus the minimum, man.
Oh.
Yeah, this is the IQR is equal to this. Range is equal to this.
Oh, okay.
Yeah.
Thank you. And also, 2019, the quiz, I do not really understand why you differentiate.
Because we asked to show that this is minimized. So to show that a function attains the minimum or maximum, you need to differentiate it.
And then set it to equal to
Set it equal to 0 and find the value of a that satisfies the equation, right? Hello, just wait a minute, okay? That's what I've done. And also you need to find the second derivative and show it's positive in order to be a minimum. If it's negative, then it would be a maximum. I thought you did this in calculus, right? In order, how to minimize or maximize a function.
I did not know it can work this way.
Yeah, any function it can work, ma'am. Yes. Yes, sir. You have a question?
I just wanted to double check on the density thing with the where's my page go? On the density thing in example 2, is it like when you said that they should all add up to 1, it's not like just the individual density?
No. It's the area. Like, you remember the picture that I showed you? Do you remember the picture? I don't know if I have it here, but I showed you a picture with this one. You see, the area must add up to 1. The area here, all the areas here must add up to 1.
Oh,
Yeah.
so would you draw it as like a curve then, where it would add up to 1? Or?
No. I mean, each of these is a box, right? So you should take the area of this box, area of this box, area of this box, and sum them up. It should be 1.
Okay.
Yeah, it's not a curve. It's still like a histogram.
Okay.
Yeah, but each of these boxes must add up to 1. The areas of.
Okay. I think I understand.
Yeah. And come again, man, if you don't. Yeah. Yes, ma'am.
Hi.
Yeah.
I just didn't understand how you got from there to there, and then that's that.
Yeah, that's because of the definition of variance.
Yeah.
Remember, you have a piece of. Okay, let me write it down here. The definition of a variance. Oh shit. Sorry. The variance of a variable x is defined as the expected value of x minus the expectation of x.
Oh, sugar, yeah.
Yeah, this is the definition.
Yeah,
now.
yeah.
So that's what I have used from this to this and this to this.
Yeah.
You can take this with you.
Thank you. What about there to there?
Yeah, that's what I would like you to show this.
Okay.
I would like you to show this. It's not trivial. I mean,
Okay.
it's something you need to
Right.
try to work on it, ma'am. And if you have problems, come and see me.
Where are you getting like adding a mu in and an n? Where does that kind of come from though?
That's something you need to show. I mean, it's not difficult to show, ma'am.
Okay.
Yeah, just work it out
you.
and see.
Thanks.
Yeah.
Thank you.
Yes.
Do we still have the lab next to it? Because
Did you look at the timetable, ma'am?
yeah, because a lot of teachers.
Yeah, there is a lab on Tuesday. Yeah, Tuesday.
So we still have.
Yeah. Yes.
Okay. Thank you.
Yeah, we have a lab on Tuesday. Yeah. Yes, ma'am.
I want to take a picture about example 1 because I can't even revise them all.
I will post it on the course website after I go home. After I go to the office. This is the example 1. This is example 1. Yeah. Sorry, ma'am. I'm just give me a sec.
Thank you. Sir.
Yeah, pleasure. No. Yeah. Okay, thank you.